as assembler processes the file that we have right here. Okay, so when we say build and the assembly gets invoked, and it processes the file, generating translating our instructions and preparing these variable allocations. It keeps the symbol table, and recall that since we created this project, and when we created it, what we added was where's my Solution Explorer? Recall that if we go to the properties here and we specify the listing file, so this listing file is still here. If you don't have it, you can add it to your project if you create a new project from scratch. And if I go to my debug subfolder where I'm building this program, here's the listing file, lst.lst. So if you take a look at the listing, at the bottom of the listing file we have names of segments that we're using. So we're using constant segments, text segment, data, and text. Text, of course, contains the code, right? And we also have a list of procedures here and a list of local variables. So far we have only main procedure, which is located in the code segment like this. And we have some information printed for these names, and so this is the symbol table that the listing file specifies. So in the lowest portion of it we have the definitions of our bytes, words, double words, and so forth, and you can also see the values that these things are using. Basically, these labels contain these values. So, for instance, if word 2, it contains 02, for instance, here. So if we scroll back to word 2, you see that this is the offset 02, right? So this thing offset into the segment, into the data segment, because it's being allocated just like this. Okay, so this is idea of the symbol table, and again the listing file can be helpful in quick overview of the locations of our variables and other types of identifiers that we're using in our program. So the correspondence to CDataTypes, again, the C and C++ do not really stick to specific sizes, but on most platforms this is the correspondence to a character, integer or unsigned integer, floating point, and the double. Okay, so these are memory allocation directives that correspond to these types. So most of the time they will work like this. And actually, we should probably indicate that this is a short integer, because this is the word, so this is not exactly an int, this is a short integer. But it doesn't matter, it's just the idea is that there is some correspondence. I think you really need to verify it. It's all platform specific, and you need to find out what directives are corresponding to your high-level programming language data types, and take a look at the sizes of both when you're making your decisions specific to this level. So this is more extended list of possibilities to write these data allocation directives. And just to browse it quickly, byte allocates unsigned numbers. Signed byte as byte is nice to use negative and positive values. So remember, if you really want to use a 2's complement encodings of positive and negative values, you should remember to do this. Just say that this is a signed version. Okay, so signed version, and then signed. You can use it everywhere, right? So if we do this, then we can start initialization with negative values like this, right? So we can say that this is minus 123 and so forth. Okay, so there are basically unsigned and signed versions of all of them, and these DB, DW, and so forth are older names for these allocation directives. And it's nice to just observe what are the ranges of the signed numbers, right? So this is like the range, for instance, here for double word, which is 4 byte size integer, is from 0 to up to about basically 4 gigabytes. By the way, this is a mistake. It's not megabytes, it's 4 gigabytes right here. So sorry about this typo. Okay. Right, and this is the way the sizes basically fit into the registers. So register EAX is 4 bytes, and you know, like a double word which is 32-bit, can be used in combination like DX and AX, for example, and 16-bit word value stored in register BX, which is 16-bit register. So these are just examples of the way the values are stored when you think about these values, how they would appear in different registers that we know them by name. So that's just a set of examples. Same idea of low bytes and high bytes, which low words and high words, which are really specific to Little Indian storage type of multi-byte values. Okay, so this is also picture taken from our official Intel architecture manual. Sometimes you don't have the data to initialize your values with, and there is even a recognized uninitialized data memory segment, which is constructed when your program is loaded into memory. And normally on most operating systems, this uninitialized data segment is written with all zeros by the program loader. But anyway, you can reserve a byte to allocate 1 byte and specify how many of them you want. So instead of thinking about some sort of initialization syntax or duplication syntax like this, what you can do is just say, I want to reserve 100 elements or 100 instances of 16-bit memory locations. In other words, this is 200 bytes. Okay, so these are directives to do something like this. So reserve byte, word, double word, quad word, which is 8 byte size, or even a 10 bytes. So this is a reserve T directive. And so this is how many of them will each contain, and you specify the number of them that you want. We have seen the uses of the pointer already. It's just another place where we specify these things. Yeah, I'll let you just read the rest of this slide. I'm not going to read this for you, and this is the code example, but we've seen this used in our samples multiple times already.